going to tell us about holographic observers for time band algebra.
Okay, so thank you very much to the organizers for inviting me, getting me entry into, giving me an excuse to enter IISc. And thank you all for staying. I know this is the last talk, so I'll try and be in time. So I'm going to speak about this paper that we wrote about a few weeks ago, and this at the end of last paper, one of the last papers of the year, that we wrote in collaboration with Christian Jensen and Anthony Speranza. So this work, I'll try and make some, unfortunately I wasn't there yesterday, but I'll try and make some links with Sunita's talk and also with Anurag's talk that we heard, and so hopefully it'll help also motivate some of the discussions that we were having earlier. Yeah. Okay, so let me start by giving you the motivation for this talk and what the broad question is going to be. So the broad question is the following. So consider some theory of gravity in an asymptotically anti-de Sitter space, and here is this boundary time band. So this is, in fact, unlike what Sunita was talking about, I'm just going to speak about empty anti-de Sitter space, although towards the last part of my talk I'll say a little bit about black holes. So consider just empty anti-de Sitter space and consider this time band that runs from minus t by 2 to tb by 2. Okay? And this tb is smaller than pi, which means that this time band is shorter in extent than the light crossing time of anti-de Sitter space. In particular, what that means is if you send off a ray of light from here, these 45-degree lines are light rays, it will reach the right side after the end of the time band here. Okay, so this is less than a maximal time band that we were talking about. I think the phrase causal depth or something was used in the first talk. So this is a case where this time band can only look so far in the bulk, the point where these two light rays intersect. And there is a region, this R bar region in the bulk, which I've drawn as a causal diamond, which is space-like to all points on the time band. Okay, so I hope the geometry of the configuration is clear. This is the geometry that will appear in most of my talk. So the question I'm going to try and ask is, how do we define, in a theory of gravity, an algebra for this boundary time band and its commutant? Okay. This is a topic that receives some attention. In fact, this work of ours was motivated by a previous paper by Christian, Jonathan Sorsay, and Anthony Speranza, where they did try and define gravitational corrections to this algebra. And as I'll say at the end of my talk, we reached almost the same result that they did, but after having to solve some puzzles. The other thing I should say is that in fact I'm not really an expert in the issue of von Neumann algebras in many ways. I've often sometimes worried that these are very abstract questions, but this question I'm going to try and persuade you about having to define an algebra in a theory of gravity is really it's really a genuine physical question, and it's not a formal issue. Okay, so the way I've structured my talk is I'm first going to describe how one would define this algebra in a quantum field theory where we have switched off gravity. And then I'll explain to you why there is naively an obstruction in defining this algebra in a theory of gravity. And then I'll tell you how we can overcome that obstruction and define the algebra in gravity. And I'll make relation to recent discussions of the cross product. And if I have time, I'm going to talk a little bit about the eternal black hole, which, as I said, will relate to some of the discussions we were having just a few minutes ago. Okay, so let me first try and explain to you how we would define the algebra of this time band in a theory of, in a quantum field theory. And when did I start so I can keep track of time? 3 minutes back, okay. Okay. So if you're just in a theory which doesn't have gravity, then this algebra is pretty simple to define. And the way you define it is you start with these operators and on the boundary. And you start with these operators on the boundary, and you just restrict boundary operators to being operators between time minus t by 2 to time plus t by 2. The way you define these operators on the boundary in a theory of gravity is you take a bulk fluctuating field, and as Anurag was just describing, you take the boundary limit of this field, you scale it up with the correct conformal dimension that gives you a non-trivial limit, and that defines for you an operator which is completely gauge invariant. invariant. When I say gauge invariant here, I mean it's an operator that does not transform under small gauge transformations, although of course it does transform under large gauge transformations. And then I can take these operators and I can restrict their t coordinate to be minus t by 2 to t by 2. And the people who like to define algebras will say, well, you shouldn't speak of this operator, but rather you should take it and you should smear it with some function f which has some support, but this support is restricted again to this time band. And in addition, you should then take bounded functions of these polynomial operators. But we'll be somewhat naive and we'll be happy just by saying that you take these operators and then you look at all polynomials in these operators, and if you do that, that defines for us the algebra of this time band. Okay. Now, I want to emphasize that you might have worried that this algebra, shouldn't make sense, and the reason it shouldn't make sense is because if you really think of the boundary theory, then in the boundary theory, there's what's called a time slice axiom, which tells you that if you look at the set of operators at any given instant of time in a theory, that set of operators is complete. Okay, that's true in quantum field theories as we consider them. And so you might have thought, if you had an ADS-CFT perspective on this problem, that it shouldn't make sense to think of algebras in bands of time, because even algebras on any cut, in fact, give you all operators on the boundary. However, in the limit where the bulk is a quantum field theory and gravity in the bulk is not dynamical, in that limit, the boundary theory is not an autonomous theory. Okay? The boundary theory is not a theory which has a Hamiltonian that can evolve you from one time slice to the other slice, and that is why this algebra makes sense. Okay? This configuration was first discussed many years ago, in fact, in work with Shouvik Banerjee and William Bryan, Kyriakos and me in 2016, and then it was revisited in 2021 by Liu and Loy Theisser, who pointed out that this algebra is what's called a type 3-1 algebra in this setup where you have a quantum field theory in the bulk, although this classification will not be so important for the purpose of this talk. Yeah. You could also, try and write this algebra rather than writing it in terms of just these boundary operators, in terms of this bulk region R. So this time band algebra, you can also think of as the algebra of this causal wedge. And the way you do that is you just reconstruct every operator in this region R in terms of smeared operators on this time band. And in this paper in 2016 that I just alluded to, we showed how you could explicitly perform this reconstruction in terms of some modes that we found explicitly. There's a slight subtlety in this reconstruction which has to do with the fact that it has to be performed mode by mode, but conceptually it's pretty simple. You can write any operator in this region R in terms of operators on the time band smeared in a particular way so that this operator phi is a local bulk operator. Okay. And so this algebra that I wrote on the previous slide as a set of all polynomials in these boundaries, I could also write in terms of the set of all polynomials in these bulk operators, but smeared with some bulk smearing function that has support in this region R, which is this causal wedge.
Is it fair to think of the quantum field theory on calculation as
Yeah.
a strict large and limit?
Yeah, it's a strict large and limit. You can think of it as a strict large and limit. That's in fact how we described it in this paper in 2016. You can do a little bit more. You can also think of a hierarchy of interactions in the bulk, where not all interactions in the quantum field theory are controlled by n. So if you did that, this would still be valid. This formula that I wrote would have to be corrected by that interaction that you turned on, the non-gravitational interaction. But really what's important is that gravity is switched off, not that the theory is a free theory in the bulk. Okay.
So I think the boundary Hamiltonian physics scale, because there will be an n outside.
Yes.
So
for that you need gravity to be switched off. The only subtle point, what you said is correct. You can think of this as the strict large and limit. The only point I wanted to make was in ADS-CFT we don't have a hierarchy of interactions. All interactions are controlled by n, so strict large and limit takes you to a free theory. You could think of an interacting quantum field theory in the bulk, and it would still be the case that the algebra in this region R is the algebra on the time band. Yeah. Yeah.
I'm starting from the boundary theory, let's say.
Yes.
I will imagine that the Hamiltonian would have an n.
Yes, I agree with you. I'm just saying that if you someday came up with the boundary, maybe the subtlety is unimportant. If you someday came up with a boundary theory which had a hierarchy of interactions, where gravity was controlled by n, the central charge had an OP, and there were other OPs which were not controlled by 1 over n, you would still be able to do this.
But do we have any examples of that kind?
No, of course not. Otherwise, we would have solved the hierarchy problem. So, yeah, so we don't have any examples in a full ADS-CFT setup. Yeah. Okay. Yeah.
The operator OT prime is not indexed by K.
The operator OT prime, no, it's being integrated. So OT prime, and then I integrate it with e to the 2 pi I k t prime by tb. So this is the Fourier transform, and then I take the Fourier transform and multiply it with this mode operator psi. Now there's also, by the way, I should say about notation, there's also a sphere coordinate that goes around the boundary, which I'm often going to suppress because it doesn't play much of a role. So this time band really goes all the way around the boundary. Yeah. So there's also a spherical harmonic that I just haven't written. Yeah. Okay, good. Very good. What about the commutant? So, you know, when you have an algebra which is a subalgebra of the full algebra, it also has a commutant which is a set of all operators that commute with this algebra. This algebra is a set of all operators in this bulk diamond R. How do you write them? Well, you take the boundary operators, but now you integrate them over from minus pi by 2 to pi by 2. So you take the boundary operators and you integrate them on a larger time band, but with a particular kernel. This kernel is the famous HKLL kernel, and you choose these coordinates that appear here on the other side to be such that TR have support in R bar. So from the boundary point of view, it looks like a slightly funny thing you're doing. You're taking operators, you're integrating them over this time band. Some of them overlap with the operators you had previously, but it does turn out that if you integrate them with a particular kind of kernel, then you do get operators that commute with all the previous operators that you had. Okay. So if you play the smear, yeah, just one second. If you play the smearing game again, then of course you can take these operators and you can smear them with functions G that now have support in R bar. And if you do that, then you can then take polynomials of those, and that will give you the commutant algebra. And as I said, this commutant algebra was shown to be of type 3-1 recently. Yeah.
Yeah, just small points.
Yeah.
So in the previous slide, when you constructed this bulk operations,
Yeah. Yeah.
you had, so you said you had an integral over R as well.
Yeah.
And you didn't have to worry about like taking R to R plus.
No. That, by the way, I don't have to do here also. I never.
Here you don't have.
No, here also we don't have to do that. This is done mode by mode, but it's really done by doing it in this way. You know, if you do it mode by mode, then this is completely fine. I don't need to. I do not have to complexify the boundary. Nowhere have I complexified the boundary. It's an integral on this. Yeah. Okay. The fact that this algebra is of type 3-1 is kind of obvious from the bulk point of view, because notice these are algebras of quantum fields in some sub-region of the space-time, and such algebras are always of type 3-1. Yeah. Okay, so this is, you know, if this was all the talk I had to give, I would be done very much early and very, very much in time. But of course, there's more to the story when you turn on gravity. So the construction in quantum field theory is completely simple. It's transparent. There's nothing to it, and it's what I just showed you. I'm now going to explain why in the theory of gravity, this construction, the analog of this construction, is somewhat non-trivial. Okay, so what is different about a theory of gravity? Well, what is different about a theory of gravity is related to the constraints that Anurag just mentioned, and it has to do with the fact that if you think of an observer in this region R, remember this region R is the region near the boundary. Okay? So you think of this observer who lives in this strip near the boundary, this maroon colored strip, and such an observer can measure the energy, but can measure the energy of the whole space-time. Okay? This is it arises as a result of the constraints that we were discussing in the previous talk, but in fact it's something very physical. It's something that's taught to us in class 9th or class 10th in gravity, which is that there's a Gauss law, which tells you that if you take the mass in a region and you integrate it over you integrate the flux of the gravitational field over a Gaussian surface at infinity, that tells you the mass of what is in the bulk. So that tells you if you have some mass in this region which looks like it's in the commutant of the time band algebra, even then you can determine what the energy of that fluctuation is by taking the metric at infinity and just by integrating it. Okay. Now, because this energy, this Hamiltonian operator, is all, you can integrate it in the R goes to infinity limit. Therefore, this Hamiltonian operator is one of the extrapolated operators, gauge invariant operators, that I described previously. So in particular, this Hamiltonian belongs to this time band algebra, because you can measure it at any time. You could measure it in particular at time t equal to 0. Okay. However, this creates a seeming inconsistency, because it tells you that if I take one of these operators in the time band, remember my objective was to define an algebra of operators for the time band, and I evolve it with the Hamiltonian, then it can take me from inside the time band to outside the time band. Okay? And one of the properties of an algebra is that it must be closed under products. But now we have some trouble, because see, we have this operator O of t, so this is t, it sits inside the time band. H is an operator in the time band. Because H is an operator in the time band, and because we are allowed to consider bounded functions of H, in fact, the people who study for Neumann algebras would instruct us to only consider bounded functions of H. So all of these are good operators to consider, e to the minus IHT, e to the plus IHT, and I can just multiply these three operators and I will get an operator in this region, but an operator in this region is clearly not in the time band. So the puzzle is, how do we define a closed algebra for the time band? And I want to emphasize that this puzzle is manifest already in the bulk theory. It's important that I did not need to invoke ADS-CFT for this. I didn't need to say that there was a CFT which was n equal to 4 super Young-Mills, which was dual to the bulk theory. All I needed to say was that the constraints of the bulk force the Hamiltonian to be a boundary operator, and that already creates a problem for closure. In particular, this problem for closure is so severe that it would tell you, remember, the way I constructed these operators in R bar was that I constructed them by taking operators and integrating them over this whole region and then smearing them with some particular HKLL function. But this kind of procedure tells you that you can take operators here, you can evolve them out of the band using this, and then you can also construct operators in R bar. So it would suggest that not only is there a problem of closure, but in fact this algebra that we are discussing doesn't have a commutant, because it's a full algebra. Okay, this figure doesn't display correctly for some reason. This is a problem with Max, actually I've known. Anyway, the problem, this is a manifestation of a larger program that many of us in ICTS have worked on. Nava is here, and the program is that if you in a theory of quantum gravity, the slogan which we sometimes use and we term it the holography of information, is that in the theory of quantum gravity, if you look at observables in a bounded subregion of the Cauchy slice, if the figure had shown correctly, there would have been some shading around this region. So that if you look at a bounded subregion of a Cauchy slice and there are some observables, for instance, maybe there are some observables which take on some particular values, then these same observables can also be accessed from the complement of that bounded region. So in this figure, imagine that there was some shading here. You could make observations in the complement of the bounded region, and you would be able to determine the values of observables here. This is of course something that's obvious if you think of a setup where you have ADS-CFT, but we've shown you can, there's a version of this which is also true in asymptotically flat space and also true in de Sitter space. But the important feature is that this is a property that's implicit in quantum gravity, and in fact it is this property that's creating this trouble for defining this algebra of a time band and telling you that it looks like you cannot define an algebra of a time band in a closed way, because an algebra of a time band in the theory of quantum gravity would be the full algebra of the bulk. Without invoking ADS-CFT, it would just from the properties of gravity be the full algebra in the bulk. So that is the physics of the puzzle that I just described. Okay, so now, of course, I'm not going to say you can't define the algebra. Yes?
Puzzle, is this also present in asymptotically flat?
Yeah, it would also be present in asymptotically flat space. The same puzzle would. You could try and ask, well, you'd have to define what a time band is, but for instance, you could say, let me take some region of scri plus and some region of scri minus and try and ask for, can I define the algebra of some segment of scri plus that includes the pass boundary of scri plus, and you would not be able to define that algebra because it would not be closed. So, I think, well, if you took, so if you took some band here, for instance, then what would happen is that this algebra would extend in this direction. So you would not be able to confine the algebra to this region of scri plus, but rather, you would be able to use what you would have to use here would be the Bondi mass. So it's a little more subtle because the Hamiltonian in ADS is conserved. In flat space, it's not conserved, but you could still use the Bondi mass to evolve you into the future, although not into the past. So you could evolve in one direction, but not in the past.
So
Yeah.
one answer,
Yeah.
would it be sensible to say, I won't include the Hamiltonian in the time band?
then you would be back to where we were, which was a non-gravitational theory.
Why you might have all the other degrees of freedom?
Well, okay.
You have the extrapolate. Is it possible?
Yeah, so you could do that. So you could do that at leading order in perturbation theory. It would be a little artificial because the Hamiltonian is one component of the metric.
Yeah,
so what you could say is, I'll keep all components of the metric, but I won't keep this component of the metric. In fact, you could do that if you just insisted on saying, I want to work to first order in perturbation theory. But then you would get into trouble at next order, because what you would find is, you take the product of two operators in the bulk, you can see this on the boundary, and you get the stress tensor on the right hand side. So now if I'm allowing you to keep this operator and this operator, then I take the product of these operators, I get the stress tensor, I integrate it, I'll get the Hamiltonian. So you'll have to keep kind of throwing it out. In fact, in flat space, it's an easier thing to do to try and throw out the operator, but in ADS, it's much harder. But maybe you could keep throwing it out. I'm going to give you a different solution, which doesn't require that, which I think is more physical. I mean, there's no reason really to say you can't measure one component of the metric, but you can measure another. LIGO can measure the mass, and we can measure the mass of the sun. Yeah. Okay, good. So the physics of what I'm about to say is that holography, these holographic properties of gravity, they're in some sense analogous to unitarity. Okay? And what I mean by that, and I'll explain in a few minutes, is that these properties are important in some regimes, but they're not important in some other regimes. Okay? So this is an analogy. I'm just saying it's analogous. I think it's a very useful analogy to think of, and I'll now explain in what sense I mean that the holographic properties of gravity are analogous to unitarity. Okay? So what is the property of unitarity? Okay, it's something pretty obvious what I'm saying right now. Unitarity is a very important in principle property of any quantum field theory. So just imagine ordinary quantum field theories. It's very important that those theories are unitary. If they're not unitary, we'll lose all sorts of, we'll have all sorts of bad things happen around us. And so it's very important that non-perturbatively, the Hamiltonian is Hermitian and everything is evolved with a Hermitian Hamiltonian, time evolution is unitary. On the other hand, we also trouble our students in our first year quantum field theory classes by asking them to verify unitarity in light excitations about the vacuum. Okay, this is the problem of understanding the perturbative S matrix. Anindo, for instance, and also Anindo and collaborators have been able to extract a lot of mileage by looking at unitarity, but in their studies, they're looking at the vacuum and looking at light excitations about the vacuum. And light just means that the excitations they're looking at are not non-perturbatively heavy. Okay. So unitarity is very important on the extreme right because it's a real feature of the theory. It's also important, when you're constructing the perturbative S matrix. On the other hand, there are obviously many regimes in which unitarity is not important. One of them is everyday life, right? It's the fact that I throw this up and I caught it, and you cannot tell me, what was the velocity with which I had thrown up this pointer, right? And that suggests that physics is dissipative in everyday life. And of course, why did that happen? We all know the answer. The answer is that there's a heavy background, which is me and everything around us, and I have coarse-grained the algebra of observables that all of you have access to. So you don't have access to all the atoms and molecules inside my body or in this room, and therefore you have lost information by coarse-graining and by introducing a background. The background is important. You can't coarse-grain if you're just in the vacuum and you have a few particles. And by virtue of that, you see dissipation, which suggests that the world around us is not unitary, but only in this regime. Okay? Of course, the world is unitary, and you can verify unitarity in light excitations about the vacuum, but if you introduce a heavy background and coarse-grained physics, then it looks like the world is dissipative. So I'm about to say that holography is almost exactly the same, which is that if you look at holographic properties of gravity, there's a regime in which they're very important, which is when we look at black hole information. As we've argued, they give us a mechanism whereby, it's not true that the outside is independent of the inside, and that's very important to preserve the unitarity of Hawking radiation. It's very important to ensure that black holes evaporate unitarily, and of course, it's an important property of gravity in many other ways, the fact that gravity is eventually holographic. It's also a somewhat surprising statement, but it's true that this holography can be verified in light excitations about the vacuum. And what that means is, you really can take small excitations in the middle of ADS. You can go to the boundary in a region that's space-like separated, and by doing perturbative observations in that regime, you can determine what is in the middle of ADS. That's a surprising fact, but it's true, and we showed this explicitly in a set of papers a few years ago. And so holography is also important when you look at light excitations about the vacuum. This should be compared to what I said about light excitations about the vacuum and unitarity being verifiable perturbatively with the S matrix. On the other hand, if you look at a heavy observer and coarse-grained physics, then you go back to a regime where the holographic properties of gravity stop being apparent, and instead gravity appears like a local quantum field theory with some tweaks, as I'll explain, just like physics appears dissipative in the same setting. Okay, so I'm now about to explain how, using this perspective, we can define an algebra for the time band in a theory of gravity. Okay, good. So the key point is going to be to introduce an observer. Okay? So the observer is something that was discussed in the morning session, and this observer is going to play the role of a background. Remember, I said we need two things to make holography not apparent. One is you need a heavy background, and second, you need to coarse grain. Okay? So the heavy background is going to be, the role is going to be played by the observer. So what is the observer? The observer is just a state in the theory of bulk quantum gravity, which has the property that it's much lighter than the Planck scale. Why do I demand that? So that the observer doesn't back react. The metric still looks like that of ADS. You could relax this condition, but I'll work with this condition for simplicity. Second, this observer has some fluctuations in energy, but both the energy and the fluctuations in energy of the observer are much larger than the cosmological scale, which in ADS I've just set to 1. Okay? So you have an observer who's much heavier than the cosmological scale, but much lighter than the Planck scale. And of course, you know, this observer is one of e to the s states in this band of energies between E and E plus or minus delta E, where this entropy is also much larger than 1, but much smaller than n. Okay? If the cosmological constant had the opposite sign, and if we lived in a world which was an anti-de Sitter world but with the same magnitude of the cosmological constant, then we could take the observer to be a virus. Okay, the observer doesn't have to be us. This figure for the virus is really something we pulled out of a biophysics paper, and it really is true that the virus is much heavier than the cosmological scale. So the cosmological scale, if you convert it to grams, you take the cosmological constant, write it as a unit of mass, it's about 10 to the minus 66 grams. The virus, on the other hand, is only 10 to the minus 15 grams. So this is a coronavirus. And the Planck scale is 10 to the minus 5 grams. So you see the virus sits smoothly between the cosmological scale and the Planck scale. Okay? So the virus could be an observer. That's all we mean by heavy background state. It doesn't have to be like the Earth. It can be the virus. Yeah.
Sorry, in your units, Planck scale is n squared or n?
Actually, I'm not being precise enough, but let's take Planck scale to be n. Yeah. I'm not being precise enough. I really don't want E to scale like any power of n, but I always like to call Planck scale n. N is Planck scale for me.
So black holes are not observers.
Black holes could be observers, but in the regime I'm talking about, black holes are not observers. Although in the last part, if I have time, I'll discuss where black holes can be observers. So the fact that E is much smaller than n is actually not so important. E is much larger than 1 is much more important.
What about asymptotically flat?
In asymptotically flat, you're saying there's no 1, right? Yeah, so it's an interesting question. We'd have to be a little more precise also about what coarse graining is, because what you're talking about is an infrared issue. What I would say there is that you introduce an effective infrared cutoff, and then its infrared cutoff is smaller than E, smaller than n, but we'll have to discuss what that infrared cutoff means. Yeah. Okay, second thing I said you need is you need a notion of coarse graining. So how do you coarse grain? Well, you allow this observer, our friendly virus, but to measure only a limited number of operators. Okay, you don't allow the observer to measure all operators. So in particular, you allow the operator to measure polynomials in these boundary operators I discussed, but polynomials where n is much smaller than the entropy that I described. As Sandeep said, we'll exclude the Hamiltonian from this set of operators for now, but it's an unnatural thing to do. So I'm going to come back and reintroduce the Hamiltonian, but for now I'm just going to exclude it by hand. Okay? Yeah. The entropy was the number of states between E and E to E plus delta E. Yeah. Okay.
Sorry, Suvrat.
Yeah.
I mean, why is this an algebra?
It's not an algebra right now, it's a set. It's a set. Yeah. So later we'll take n to infinity and take all these things to infinity, in which case it will become an algebra, but I'll also include the Hamiltonian when I do that. Okay. So later I'm going to take this limit. In that limit, this cutoff goes away, it will become an algebra. When I take the limit, it's important to preserve this hierarchy, that I take first n to infinity, then s also goes to infinity. As I do that, I keep E by n always small, I keep delta E by E small, and I keep n by small. So I have to take the limit in a particular order for this construction to all make sense. Yeah. They can be observers, yeah. I'll come to it at the end. They could be observers. I'll describe, yeah. Okay, so the set of all these observations that this person can do is in fact well thought of as the little Hilbert space that we introduced a long time back to discuss what an observer could do about a black hole, and that is that the observer themselves is in some state which I called psi, and then you can act with elements of this state that I discussed, which are A1, A2, and that gives you a subspace of the big Hilbert space. You can't draw it really, but what is meant here is that the subspace is very high codimension. You can't really explore all the possible directions. There are e to the s directions in the full Hilbert space, but you are only able to explore a small subset of them, and that's why it's a little Hilbert space. Okay. I'm also going to introduce what is called the modular operator, which I won't discuss much because Sunita already discussed it, which is just an operator that satisfies the property that if you take two operators from this set and you introduce this operator delta, it reverses the order of the operators. You can just take, if you have not seen this operator below, this to be the definition of the operator delta. Okay? It just defines the action of this operator on all elements of the little Hilbert space. Okay? Now, one property of this operator is that in this limit where n goes to infinity, this operator generates an automorphism of this algebra, and this is called the modular automorphism. Okay? Which means that if you take an element of this algebra and you evolve it with these unitrys, you get back another element of the algebra. Okay? Okay, good. Now the key property of this state that I'm going to need is that if you take this state and you time evolve it with the Hamiltonian,
So n is small n is much less than
S, much less than S. Yeah. So if you take this state and you evolve it with e to the minus iht, then a key property of this state that follows from all the properties that I mentioned previously is that you get a new state which is almost orthogonal to the previous state, provided you take this time interval to be much larger than 1 over the gap in energies. Why does this happen? It's very easy to see why it happens. Imagine that this state is a linear superposition of different energy eigenstates, and I evolve it with e to the minus iht. I put phases in front of all the different energy eigenstates, but because my time is much larger than 1 over delta E, these phases are just a lot of random phases. Right? And then if you take the inner product with the original state, just by the fact that you have all these random numbers and you have cancellation, the sum of n random numbers is of order of magnitude square root n, you will find that these states are almost orthogonal. Okay, so this inner product will become e to the minus s by 2. Okay. Therefore, the action of time translation on the little Hilbert space that I discussed generates a larger Hilbert space, which is parametrized by the value of the time that I translated it by. You have to construct the space slightly carefully because the way I've described it here, it's a discrete space. But you can see that by virtue of this property of the observer state, you get an additional degree of, you get a one parameter family of little Hilbert spaces, which are labeled by this T. Okay? Right now this is just an auxiliary T, but this is going to turn out to be important to define the time for the observer. Okay? So this one parameter family of little Hilbert spaces is parameterized first by the, you take the original state, you can act on it with an element of this small algebra that I discussed, and then you can act on it with this e to the minus iht, and these together generate for you the space of states within which we are going to discuss all operators.
Really sorry.
Yeah.
What is capital S?
What was?
Capital S.
Capital S was the entropy. It was a number of states between in the energy E to plus minus delta E. So it's the number of states around the observer. The full dimension of the Hilbert space is e to the s, of which you're only exploring a small.
Okay, full, yeah. And a little n is also how many operators?
Yes, how many operators you can have, exactly. Okay, good. So this is actually the key formula. So this is how you define an operator which stays within the time band. So let this PT be the project. This is perhaps the only technical slide I have. Let PT be the projector onto a particular time in this bigger Hilbert space. Yeah, I'm about half an hour through. Is that right, Chair? Yeah, okay. So let T be the projector on a particular time in the bigger Hilbert space. Okay. Then take an operator which was part of this set of light operators that I discussed and write down this formula. Okay, what does, just look at, I'll explain why the formula works. But this is a particular deformation of the original operators. This is not the original operator. A is one of those polynomials of those boundary operators. I take it and I insert it into this formula that involves this projector P. It involves these actions of the Hamiltonian and these modular operators and also an integral over T, and I call this operator A hat. Okay, this formula we in fact wrote down in our construction of operators in the interior of the eternal black hole many years ago, and more recently Kyriakos and collaborators also used it to construct quasi-local operators in ADS-CFT. So this is a formula that has appeared previously in the literature, not in the context of discussing von Neumann algebras, but just in the context of understanding locality in the bulk. So right now this formula might look a little mysterious, but I'm now going to explain these two equations, which will explain for you how this formula works. Ket TT is just this time. So remember this you have a larger Hilbert space which is generated by a value T and an action of the algebra A. In fact, if you take the set of all such Hilbert spaces, no. So there are two directions you can move. So you can take the state psi. Can you see? I don't know. And you can act on it with an operator A. Yeah? Okay, great. That's fine, yeah. So you can act on it with A. Or you can do A times e to the minus IHT. Okay, so you can do time translation and then act on it with A. Okay. A is one of those small operators. So H was not one of them. So if you want to act with the full algebra, because I had excluded H, I can act with A or I can act with this. So I get, this is what I'm calling the state TA. Okay. Now it turns out that this state takes the form of a direct product, which I haven't explained, but it does. And so you can talk of a projector onto the time T, which means you look at all states A, but you've fixed this part of the action. Okay, or you can move. Is this clear? Okay, good. Thank you.
Once again,
yes.
What was little a?
Little a was one of those boundary operators.
The ones you started with?
Yeah, exactly. Those operators. The ones which transform badly under the Hamiltonian. So that's little a, which I'm now converting into a hat. Yeah. Sorry, could we switch off this? They transform badly in that they're not closed under the action of the Hamiltonian, no? Yeah. So they go out. So by themselves they don't give an algebra.
So I thought you just go out, but then you project back after cause graining. Is that what it is?
Well, so that's this. No. This formula is telling you what you do. So it's this a hat that's actually going to give you nicely form. So the physics interpretation is that let me say to the end.
Coarse graining, I would say.
Yes.
Go out and coarse grain and come back.
No. It's not so simple. You can't coarse grain an operator back in time. So I'll let me explain the end of this slide what the physics is. Yeah. But let me first explain the formulas and then I'll explain how you should think of it. Okay. So imagine you act on the original state where you had not acted with e to the minus iht. It's dark, but this is just a state where you don't. It's the original state where you didn't time translate at all. So imagine that you act on an original state. Then what happens? This PT just picks up t equal to 0, right? Because these states are almost orthogonal to each other. So this projector just picks up the value at t equal to 0. So the whole integral collapses onto t equal to 0. So all these things just don't count at all. E to the iht is 1, this is 1, everything is 1. So you just get the action of the original operator, the undeformed operator, if you take the original state acted on with some other element of the small algebra. Okay. On the other hand, imagine that you take the state and you act on it with e to the minus IHS first. So you try to take the state and I say, I'm going to try and evolve it out of the time band by acting with e to the minus IHS. But now look what will happen. If you act with e to the minus IHS first, then what will happen is you will pick up just t is equal to s. Then this factor of e to the iht will cancel your factor of e to the minus ihs because you've picked up the value t equal to s. So this will undo this e to the minus ihs, and then you'll just get a delta to the is and a delta to the minus is. And then you'll push back an e to the minus ihs, but this will be cancelled by this plus e to the ihs. So this tells you that time evolving this hatted operator is like doing a modular transformation to this operator. Okay? So I have generated a set of operators so that time evolution is acting like modular transformation, like the modular automorphism. Okay, so the algebra of deformed operators is closed under the action of the Hamiltonian, as I've just shown you. Now you can ask, what is the physics of this? The physics of this roughly is that you took these operators, and these operators were gauge invariant because they were dressed to the boundary time. So this is the answer to Sandeep's question. What we have done here is we have redressed the operators. So we have taken the gravitational Wilson line, and rather than running it to the boundary, we are running it to the observer. And by doing that, when we act with the boundary Hamiltonian, the observer, these states don't evolve. Actually, we've done something a little more complicated, which is hard to describe in terms of gravitational Wilson lines, because what we have really done is we have taken these operators and ensured that boundary time translations act in some modular automorphism way on these guys. But if you just forgot about the modular automorphism, it's like taking the Wilson line and shifting it from the boundary to something else. But the modular automorphism is more hard to describe in terms of Wilson lines. The modular automorphism in some simple cases could be the boost, but here it's just the modular automorphism. It's just by some automorphism of the algebra. Yeah.
So still, sorry.
Yeah.
So you introduced an observer in the original causal wedge of the time band you were.
Yes, yes. And then I introduced these auxiliary set of states. And that gave the observer a clock which was independent of the clock on the boundary. The way the observer can tell time is by detecting the state, PT.
Sorry.
Huh.
So you have the observer.
Yes.
Now these few states are what? Internal states of the observer. Can I think of it like
They're states of the observer excited with one of my operators on the boundary. So observer is one state, and then I can excite it with the boundary, or I can act with e to the minus IHT.
excited on the boundary can also mean excited by the bulk observers.
It could be. You can think of it that way, but the bulk observer is really just a bystander. Its only role in life is to ensure this orthogonality of time translated states.
Why is it a bystander? It's crucial for everything.
No, it's only crucial for this property, which is the property I showed here. This is the only property the observer is helping us ensure.
But can't I put it like this?
Okay, put it like that. Let the observer, let the observer be the agent.
He's got a little
Fine, he's got a little
I
hilbers.
want it to be not too big. I'm willing
Fine,
to
fine.
not to
It's fine,
I have the silver.
Fine, yeah.
I dress everything to that observer.
Yes.
And now you're saying, okay.
Yes,
you know,
that's right.
how I'll grab it.
That's the way, that's correct.
And now tell me what is the answer? I mean, okay. So
Well, let me go to the next slide. These are these operators which would be dressed just to the observer. So, if you took your operators and you dressed them just to the observer, you would have written down these operators, which are the operators of the commutant of this algebra, which are, I'm saying it, I'm removing the modular automorphism because it doesn't appear here. So, you take these bulk field operators and you write down this formula, which is e to the minus IHS, e to the HS with this PS. What this formula does is, if you act with the boundary Hamiltonian, the operator doesn't transform at all. It just sits to where it is. Sorry, there should be a hat here, which I've forgotten. The hat is missing on the right hand side. But this operator is just frozen. It doesn't move under boundary time translations. So, this operator has a separate notion of time. How does it know which time to act on? It knows which time to act on because it can detect the state. It has this notion of detecting the state. You can think of this as redressing the gravitational Wilson line from going to the boundary to going to the observer. Okay? So this operator just doesn't transform under boundary time evolution. The operator I wrote in the previous slide was slightly more complicated because it did transform under time evolution, but as a modular automorphism. So you can't think of it so simply in terms of Wilson lines.
you have a formula for delta.
Yeah, delta was defined here.
That's a formula.
Well, so in actual case, you can't compute delta for the time band, for instance. It's very hard. You can write down a formula, but you can't find delta in a closed form way. It's a question of finding the modular automorphism for a general case, except for simple cases like a ball, we don't know how that works. What do you mean? Here, this is all we needed here. This is a definition, no?
Just a bunch of definitions.
Sorry, not a bunch of definitions. What is the objection? I'm not understanding. This delta is defined, let me define the delta this way. This is my definition of delta. Then I can show under this definition, this delta is a modular automorphism. Okay. Then the main point here was to make sure that the action under e to the IHS acts like the modular operator. For this, I don't need to know what the modular operator is. I'm defining an operator which says that the action acts this way. In fact, there's an ambiguity in this definition in that I could have made time translations act as any automorphism I liked. You could have made this automorphism 1. We are just choosing the modular automorphism to make link with the literature and algebras.
I guess the point is the existence of such a delta.
Oh, certainly it exists, because this is a definition which acts on all elements of the Hilbert space. So it's explicitly defined by defining its action on the basis. So this, you can take this to be the definition of delta. This defines the all matrix elements of delta. I can specify matrix elements any way I like. So it always exists. Whether you can write it in terms of elementary fields is a different matter. But these are all matrix elements.
So
yeah.
you must go on.
Yeah.
Please excuse me.
Yeah.
But what was the need for this additional modular boost?
Yeah.
Already managed to define
You didn't need it, so there's an ambiguity. So for instance, you could have chosen these operators to define them without this delta. Then we would not have been able to make contact with the literature on the modular cross product. So in fact, in this construction, this is a good point, the construction that we have just written down, you could have chosen to include these operators, or you could have written down any other unitary operator that you liked, any other unitary automorphism. And then you would have got this other unitary automorphism on the right hand side. To make link with the type 2 constructions that have appeared in the literature, we are choosing this to be the modular automorphism. But this is not important. I could have chosen this to be 1 for just the purpose of defining the algebra. Okay. But then it would not be a type 2 algebra, it would be a type 3 algebra still. Yeah.
I mean, in some recent papers of Lashkari, he was talking about, I think, some operator slightly smeared along modular time, which I think they called Tomita operator or something.
The Tomita operator is usually just S.
Yeah, the S. No, but it's not a, it's a
No, you'll have to tell me later. I don't know what these things are. Okay, good. Let me now make link with the cross product. So these formulas, as I said, had appeared before in the literature. Now it turns out that you can write down the same formula that I wrote previously. I won't go through details since I'm running out of time. As a unit, these hatted operation as a unitary transform of the original operator with a unitary operator which looks like e to the I h minus q hat on this time operator t, which measures things here, and this modular operator raised to the time operator. So remember, the fact that the states were orthogonal, which is what the observer ensured for us, allowed us to define this time operator, which I've already made reference to. You can also define the conjugate of the time operator, which is this operator q hat. How do you think of q hat? You can think of q hat as an operator which is just sensitive to the energy of the observer. It doesn't see the energy of the small excitations about the observer. So this is a coarse-grained version of the Hamiltonian, which just sees the fact that the observer is so much heavier than the small excitations, therefore it only detects the energy of the observer. In any case, in the definition I gave you, you can just construct this operator q hat explicitly as the conjugate to this t hat, and then you can check, although I won't show it now explicitly, that this complicated formula I wrote using projectors and so on was just a unitary conjugation of the original operators with this operator v. Okay. In addition, this algebra, apart from these operators, also consists of e to the minus iht. Okay. So it's not the original operators a with e to the minus iht, but these deformed operators a hat with e to the minus iht. The commutant you can think of as conjugation with this other unitary operator w, and this is so these HKLL operators conjugated with the w, and then by inspection you can check that there's an additional operator that needs to appear in the commutant, which is a combination of this q hat and this modular operator. Okay. This in fact turns out to be the same as these modular cross product algebras that have appeared in the literature that were described in the previous work by Jensen, Sorsay and Speranza. And the point is, if you have a unitary representation of an algebra, I can act with a unitary and obtain a unitarily equivalent representation. And this time band algebra you can think of as being spanned by operators which look like a times e to the I q hat t and delta to the minus it. And here the original Hamiltonian, originally you would have thought of these operators as being spanned by a e to the minus iht, as I've written on the board, but h here has been replaced with q hat minus the modular Hamiltonian. Okay. So this deformation procedure that I discussed is the same as effectively replacing the Hamiltonian with a coarse-grained version, which is q hat minus the modular Hamiltonian, and the commutant is this algebra. Okay, these are precisely the algebras that have appeared in the literature on von Neumann algebras recently, that many of us, including Sunita, have been involved with. The point here is to show that these previous formulas that appeared in the discussion of the construction of local operators turn out to be the same as these formulas that have appeared in the recent discussion of cross products, although it was not noted earlier that this was the case. Okay. So, this was already discussed a little bit in the morning, so I don't have to say much. in general, there's been this discussion of these type 2 algebras, which are obtained by taking these type 3 algebras and taking a modular cross product. In fact, that's the reason this delta operator, we put in this delta operator, because the only way you get a type 2 algebra is if you take a type 3 algebra and do a modular cross product, okay, not some other cross product. And in fact, we proved a theorem demonstrating this. With this, you can define a density, a notion of a density matrix, and also a trace in these type 2 algebras. And you can think of these, this trace as roughly thinking of, well, you can use this to also define an entropy, which is what has been of interest. But this entropy is something that you can think of as being the part of the entropy that doesn't keep track of the universal UV divergence. So you can think of it as a UV subtracted entropy. Now, what is important in this construction, maybe one physics point that came out of this, I won't say much about the entropy in this because I want to say a few words about black holes. One physics point that came out of our discussion is that this entropy is really a coarse-grained entropy. It's not a fine-grained entropy. It doesn't keep track of the microstates of the observer. So you should not think of these type 2 entropies as keeping track of the entropy of the black hole. You should not think of these type 2 entropies as giving you the page curve of black hole evaporation or anything like that. They only make sense in a coarse-grained sense, and the whole construction breaks down if you try and push this entropy and try and convert it to a fine-grained entropy.
Let me ask you one thing.
Yes.
So, just in simple-minded terms, okay, you had some additional module.
Yes, yes.
But it seemed to me you had to introduce an observer.
Yes.
And basically, what you've defined are related to operators corresponding to measurements the observer can do.
Yes. Yes, and operators which are gravitationally dressed also in a particular careful way. And this gravitational dressing is also a standard gravitational dressing that has appeared in previous construction of local operators. And the other point is to show that this is the same as a modular cross product, which has appeared in different notation. So with some translation of notation, you convert the formulas for quasi-local operators that appeared previously into formulas for this modular cross product.
Fine. So,
yes.
But, can I just think of the entropy as the entropy corresponding to this sub-algebra? I've used the word sub-algebra.
Yeah, small excitations.
That corresponds to measurements the observer can do.
Yes, exactly, but not the density of states about the observer themselves. So this is the density of states in the effective Hilbert space.
Yeah,
this is important when people discuss black holes. You shouldn't think of the type 2 entropy as counting the UV degrees of freedom of the black hole. That's all.
I've long since given that up.
Fine.
The observer was so crucial.
That's all. Exactly.
All that silly virus can measure.
Exactly.
The entropy with
Exactly.
algebra.
That's right.
Can I say?
Yes. That's right. Yes. Yeah, that's right. Exactly. Okay, let me say a few words about black holes. I know I'm over time, but I'm going to stop very soon. But this is related to the previous discussion we had. So I want to say something about the eternal black hole. And I want to say once again, as Feynman said, same equations often appear in very different systems. How in this system also we had the modular cross product, although this was discussed 10 years ago in very different notation. But it's also related to the previous discussion. So, consider the thermophile double state that Anurag described, and further consider these large diffeomorphisms. I frankly didn't know you were going to show this figure, but this is really the same figure that you just described, although here I've moved the left boundary rather than the right boundary, but you can also move the right. In fact, I think I wrote down the formula for the right, but I've moved the left boundary in the figure. Okay, anyway, you can take the thermophile state and you can act on time translations on one side, okay, not on both sides. This gives you a new family of states which are not the thermophile's double state. In fact, they are almost orthogonal to a thermophile double state. The overlap of these states, the mod square of that is what's called the spectral form factor. However, importantly, these states have the same intrinsic bulk geometry as the original state because you just acted on them with a large diffeomorphism. So anything that you measure that's intrinsic to the bulk is the same. Okay. So we were studying these 10 years ago because we wanted to say that if the thermophile double state is a smooth state, this was the time there were discussions of firewalls, then these time shifted thermophile states are also smooth states. They also do not have a firewall. Okay, and we already discussed them in detail. You can think of them in this way. Okay, good. Now, notice the following. Imagine you have an observer who falls in from the right. Okay. Now, we can do a gauge fixing as Anurag described, but alternately, you can fix the coordinates of this observer by shooting light rays. So, this observer is falling in and is shooting light rays back to the boundary, and so using that you can parameterize this geodesic that the observer falls in a gauge invariant way. The gauge invariant way we are choosing is not by fixing a gauge, but just by saying you in a relational way to the boundary. Okay. Now here is the important fact. Okay. If you look at this operator, this observer who falls in from the right side, then you can show that by virtue of how you fix these coordinates, if you acted with a large diffeomorphism on the right hand side, then this observer's field that this observer measured is always shifted by the parameter of that large diffeomorphism. On the other hand, if you acted with a large diffeomorphism on the left hand side, that large diffeomorphism doesn't affect anything in the trajectory of the right infalling observer. Therefore, these operators have to commute with the left Hamiltonian, both outside and inside the black hole, and this is very important, that they have to commute both outside and inside the black hole. And why is that? Well, it is because if they didn't commute with the operators, with this operator, then you could show you would in fact get a firewall. Okay? You would get a firewall because if you had operators that failed to commute under the action of the left Hamiltonian, and you did. This is why I was troubling Anurag. And the reason is that if we think of operators which are just constructed using the naive HKLL construction as AL, operators in the left plus operators in the right, then they will not satisfy this property. And if you do that, you will find that you will break the entanglement between the right and the left by doing this one-sided translation. Okay. So you can show that the operators have to have this property for all these states to be smooth. And then, if you just did the naive HKLL construction, so HKLL themselves constructed these operators in this coordinate system when they wrote the initial papers, and their answer was you write the operator outside in terms of the right modes, you write the operator inside in terms of the right modes and the left modes. Okay? So you can write down some mode functions by solving the Klein-Gordon equation, and they wrote the operator inside as right plus left. And this is region 1 plus the forward region, this is the horizon. I am not here referring to the region on the left. Okay, just the region 1 and the forward region. So this was their construction. However, if these O tildes were just left operators, they would not have the property of commuting with the left Hamiltonian, which you need to make sure that all these states are smooth states. So how do you do that? Okay. Well, the answer is that the correct reconstruction is given by taking the right operators, taking the left operators, and dressing them in a particular way, redressing them. So you take HR minus HL, you introduce this time operator. This time operator is the same operator that I introduced here, but here to answer Chetan's question, it's the black hole that's the observer. The black hole is the observer. Time translated versions of the black hole are orthogonal to the original black hole. That lets you introduce another time operator. And so you take the left operators and you dress them in this way. And if you do that, you get operators that are dressed to the right boundary. Okay? So here I chose to dress operators to the right boundary. If I chose some other gauge like this maximal volume gauge, I would get a different dressing. But it's important that we have to have factors of this kind, and what precise factors you get depend on the gauge that you have. Yes. Yes, please.
I think this is a bulk action that you're...
There's no action here, it's just an operator.
You took me to the IH.
No, this is a boundary operator.
This is a boundary operator.
HR and HL are all boundary operators.
TR omega is in the interior.
TR omega is in the interior, but it's a coordinate. Remember, TR omega is all related to boundary operators in a mode. It's just a rewriting of boundary operators. So everything here is a boundary operator with a linear transformation.
Hamiltonian action of the boundary operators left or right to continue into the bound.
No, it's fixed. In this case, it's fixed because you know how these modes transform under the Hamiltonian action. The moment I write down, you see, if you look at e to the IHT, that's an operator in the Hilbert space. It transforms in this in a given way and this O tilde in a given way. It doesn't talk to these mode functions. So the action of e to the IHT only cares about the modes. So the moment I wrote down the mode expansion, which is what we were discussing previously, you fix the action of how e to the IHR and e to the IHL act everywhere. Once I give you the mode expansion, it doesn't care about the mode functions, only cares about the oscillators. So you have to change the oscillators themselves. You can't use the left oscillators, but rather you use this combination where you take the left oscillators and then you redress them. So this is a subtle point, but it's a gravitational effect. This corresponds to fixing gauge in a way that's different from the way you fix gauge. This is fixing gauge to the right boundary, where you discuss all operate. So it only works in the forward region and this region. You could fix gauge in the other way you discussed, and we could ask what the analog of these factors were, but there should be analogs of these factors. You might probably get analogs of these factors on also this side and this side. So you would get a more complicated expression, but these factors will be required, I think. This is yeah.
You must want to,
Yeah.
I'm really sorry, I've never
Yeah.
understood your mirror construction as well. So let me ask it now.
There's no mirror construction here.
This is, okay.
Yes.
Suppose I'm a dumb guy. Okay?
Yes.
I solve the Klein-Gordon equation and I mode expand in a set of modes which are nice and smooth. They are cross-cull lines.
Yes, yes, yes.
They cut across the horizon.
Yes, yes.
Now, I bring that into this wedge region.
Yes, yes,
Doesn't
yes.
involve the
Yes,
forward, okay?
yes, yes.
Now, I just look at them.
No, it would be wrong.
At both ends.
It would be wrong.
Why would it be?
It would be wrong for the following reason. You see, there's an important fact that this e to the, I'm sorry, I'm done actually, it's just post-talk discussion.
I can ask you.
No, I can answer this. You see, it's this fact. It's the fact that e to the I, HR or HL, I can write in this way, as a smooth action in the bulk. In a quantum field theory, that's not what would happen. In a quantum field theory, if you acted with e to the IHR, it would create a kink.
Yeah, I don't want to do e to the minus IHR at all.
Huh?
Okay, let me complete this.
Huh.
I take a nice crustal slice.
Yes.
Okay? I mode expand solutions to the Klein-Gordon in that. I just bring the entire slice down into the bifurcate slice.
If you took the end, if you you bring the entire, if you did a Kruskal expansion, well,
And I bring it down, and
Yeah.
there I look at it in the extra.
yeah, you might be able to do that. Yeah, that might be something you might be able to. Let's see. No. If you it might be you could do that, but of course, if you did that, the extrapolate dictionary that you would get would then be different. I think. It should not be the case in this formula that operators here are only left operators and these are only right operators. You see, if the operators in this wedge are left operators and these are right operators, these come from the right CFT. If I do e to the IHR, these operators will not transform. So whatever you need to do, you need to make sure that operators here are not just related to this left CFT, but are related to a combination of left and right in all the wedges. Okay. So if you do HKLL by solving in these coordinates that are adapted to these patches and then try and put them together, you will find there's a problem here. Yeah. Okay.
But here also,
Sorry, can I just maybe I'll complete. Huh?
here also you use some antipodal maps.
What antipodal map?
To bring, whenever you go inside for a
The question is just in this wedge, are the operators OL or are they OL plus OR? Same here in the, so in the original formula that HKLL wrote, the operators here were OL, these were OR, these were OL plus OR.
I'm saying that these OLs cannot be just OLs because you use that.
Yeah, let me just stop. I
Which is, I think that what Splenda and Anurag are doing is the analog of some nice slicing and a Kruskal-like kind of slicing and then bringing it.
Perhaps we could do that, but this was why I was bugging Anurag and about whether the operators here are just OL or not.
Okay, that should be fair.
So they should not be just OL, and these operators should not be OL plus OR. So you need some. Now it's a subtle point because you would break the extrapolate dictionary on the left hand side. You cannot demand the extrapolate dictionary itself will now depend on what gauge you have. Okay, let me. This is just what I said. This is an overview slide. I'll just say 1 minute of overview and stop. I started by talking about the algebra in the QFT, how to define this algebra of a time band. I said you could define the algebra easily in a quantum field theory. In a theory of gravity, there's a puzzle because the Hamiltonian is an element of the boundary. You can use it to evolve out of the time band. Then I said you could define the algebra in a theory of gravity by coarse graining and by introducing an observer. That's important. It's important because holography is a property that's intrinsic to gravity, and to define these time band algebras you have to go away from holography, which you can do in the presence of a background and by coarse graining. And then I showed that these algebras, once you define them this way, were the same as the cross product that has appeared in the literature. And I pointed out the cross product has also appeared in older formulas of the eternal black hole. Although we didn't write it in this language, the formulas we wrote are exactly the same as this, and this makes it obvious that this is also a cross product.
And
Okay.
HR minus HL is the model.
HR minus HL is the modular Hamiltonian, exactly. So in this case, it's just obvious that it is exactly the modular cross product. We wrote it with the projectors and so on, but in the modern notation, you could write it this way. Yeah. Okay, let me stop here. Thank you. Sorry for going a little over time.